So for most of this, we're not going to need to worry about HTML or CSS. We're going to leave our canvas blue for the moment, and we're just going to concentrate on JavaScript. I'm going to start by pasting in some Bootstrap code. And let's go over this right quick. At the top, we've got our little config object. The only value in this right now is frames per second FPS, and it's set very low to 3 because we're recording a video and we're going to use, the first thing we're going to do is be putting some output to console, so we don't need a high refresh rate. We've got our selection of our canvas. We're setting the height and width, and then we're grabbing our 2D context. We're going to add some line styling settings in here, which basically say when we draw a line, if it's a thick line, it's going to have rounded edges instead of square edges. That'll come into play later on. Now we've got a utility function called rand_range. All rand_range does is picks a random number between a minimum and a maximum. You can see it's very simply taking math.random, which returns a float between 0 and 1, and it's multiplying it by the size of the range, which is the max minus the minimum, and then adding the minimum. Very simple math. We're going to initialize and basically get things started. The first thing we're going to do is represent our mouse position with a vector. We can use two-dimensional vectors to represent any kind of x and y information. It can be acceleration, it can be velocity. In this case, it's position. And the x and y numbers are going to represent distance from this point right here, this upper left-hand corner is 0, 0. X increases to the right, and y increases from top to bottom. In computers, graphics are typically represented this way, which is opposite on the y-axis from what we're used to maybe in math, whereas y increases from bottom to top. We're going to use window.setInterval. Window.setInterval uses, for its timing, it uses milliseconds. So we're going to say 1,000 milliseconds divided by our frames per second. And we're simply going to pass in a function that will log our mouse coordinates. Mouse X, mouse Y. We're also going to add an event listener that whenever we move our mouse in this canvas, we update our mouse X and Y. This is the code to do that, where we're simply taking our client X and client Y, which is a more absolute position, and we are subtracting that relative to the rectangle, which in this case is the canvas rectangle, again defined with 0, 0 up here in the upper left-hand corner. And finally, we're adding a click event. Whenever we click with our mouse, we'll see console.log click. All this together is basically all the sort of user interaction that we need. Everything else is going to be concerned with drawing on the screen. So let's go ahead and run this, and we're going to also pop up our console here, and we can see that our mouse position is updating every third of a second, more or less. When we click, we see a click event down here. And those click events are still interspersed with this once every 3 times a second sort of loop. Alright, so let's make this do something. Now that we've got our basic user interaction wired up, that is our mouse events, and we've got a nice big canvas to play with, let's go ahead and create some particles. First thing we're going to do is add a couple new config values. Particle count is the number of particles, and then radius is a range object specifying a minimum of 1 and a maximum of 5. Next, we write a function called makeParticle. This function just spits out particle objects. It's not a constructor, but it does return an object. This particle object right now consists of POS, which is the position, and radius, which will be some number between our minimum and maximum in config.radius, in this case 1 and 5. The vector is created using vec2d.float32 vector, which is a constructor, and will return a vec2d vector object. Our position vector is an offset from the origin, which is up here in the upper left-hand corner. Computer graphics often have the upper left-hand corner as 0, 0, and the y value decreases as you go down. Next, we use our makeParticle function to populate an array of particles, just using a standard float. Next, we're going to build a function that draws our actual particles. This is our first encounter with drawing on the 2D context of our canvas, so let's take it step by step. First, we have context begin path. This tells the context that we are starting a path. The path itself is not going to be drawn until we call the fill or stroke commands. On our next line, we create an arc, and that arc goes fully from 0 all the way around the circle and back again. It's measured in radians, so 360 degrees is 2 pi. Next, we're going to set our fill style as being black. This says that when we do fill in our path, we want it to be black. It's important to note that at this point in time, we've drawn nothing to the canvas. That doesn't happen until we call context.fill. All right, so we've got our function to draw individual particles. Let's now write a couple lines of code to draw all the particles in our collection. We're using underscores each function here, which looks a lot like JavaScript's array.prototype. Either would work. All we're doing is for every particle in our particles array, calling draw particle and passing that particle. So let's see it in action. And here we have our varied particles. We're only drawing them once now, but this is going to be an animation. So we're going to go ahead and wrap this in a function that we're going to call step. And rather than calling this console.log, we're going to replace this inline function call altogether right here with just a reference to our step function. You may notice that we've got a .value call at the end here. That's maybe not strictly necessary. Yeah, it seems to be working just fine without it. In fact, now it's working about 3 times a second. This step function is now being called on our interval. However, back to the value. Calling .value here makes sure that underscore knows you're done doing your manipulations to the collection and to execute the actual chain of functions that you've passed in. Underscore is pretty good about knowing when to do this implicitly, but sometimes we have to explicitly call value, and it's not a bad habit. What's important to note now is that our console is not updating anymore because we've replaced our step function. If we click, we will get console updates there, but no update over mouse position. And even though you can't see it, these dots are being drawn on the screen 3 times a second, which seems kind of silly now, but we'll make the move soon enough. All right, let's make our particles a little more interesting. Let's make them colorful. Let's give them some alpha values too, some transparency values. So first thing we're going to do is add these kinds of things to our config. All right, we're going to add 4 values to our config. They're each range values, just like radius. Alpha goes from a minimum of 0 to a maximum of 1 in the way we're going to be using it. We're going to be using a CSS style RGBA color definition that takes red, green, and blue channel values anywhere from 0 to 255, and an alpha value from 0 to 1, like a float. We want all of our particles to be visible, so we're going to go from somewhere like 0.5 to 1. At the same time, I like sort of a bluer cast to our particles. So RG and V, we're going to do our red and green channels are going to be anywhere from 64 to 128, but our blue channel is going to span from 64 all the way to 255. Per each particle, we're going to select these random numbers. Next, we want to set up our make particle function to go ahead and initialize these values. The values returned will be RG, B, and A, and we're going to set those all up using our rand range. I'm using math.floor for RG and B to give us whole numbers. I'm not certain that this is actually necessary. And then the alpha, of course, is supposed to be a float value. Now to draw the particle with color, we're going to have to modify our draw particle function. Fill style right now is set to black. Like CSS, we can use values like black. We can use values like FF000, 0 to give us a pure red, or we can use values like RGBA and then 25500 1.0 to give us also a pure red at a full opacity or 0.5 for half opacity. We can't hard code this here though, where all our particles will be the same color. Let's see that run. There we go. They'll be that red, and you see them fade in like that, which is pretty cool because right now they're being drawn at half opacity on top of each other every third of a second. But let's go ahead and draw these at random colors. We're going to go ahead and set our alpha, actually 1 at a minimum, 1 at a maximum, because we're not moving these particles around at all. So after a few frames, they're all going to be full opacity. But what we need to do is we need to write a function that's going to generate this string for us. We could just write a big ugly function with lots of string appends, but Lodash gives us a better option. Right up here toward the top, we're going to create a variable point fill. That variable is actually a function. We, again, could write a function called point fill, which uses all kinds of string concatenation to construct this string, but it's much cleaner to write it out this way. So what template is doing is it's creating a function called point fill in this case. It's creating a function that will take in any object, and in that object it expects to see the values R, G, B, and A. We're passing in a point object, so that works just fine. And anywhere you see this square $ curly brace notation is when our string is going to be reaching out to the passed in object. So point fill is a function. Once again, we're going to go down here, and where we have our fill style, instead of having a static string, we're going to make a call to that point fill function. And we're going to pass in our point. And that will give us some very differently colored particles here, which all look kind of washed out because we've still got a blue canvas background. Let's go ahead and get rid of that. We don't really need it to be blue to display what's going on anymore. Pretty cool. Got these nice tones, cool tones. Got some reddish going on here, but mostly weighted to our blue scale. Let's do something more interesting with our mouse click function. Right now we're outputting to console, and yeah, that's not very exciting. If these were numbers or strings, we would have to use we would have to pass in the additional parameters for the index and the array itself, but we don't need to do that here. All we're going to do is increase the radius by 1, and we're also going to change the position here by 2 on the x and minus 3 on the y, which means they're going to travel to the right and they're going to travel up. And then next we are going to simply come down and replace this inline function call with a reference to grow. So run this. You can see now that when we click, each of these particles shifts up, shifts right, and grows. But we're getting this sort of after image. We're drawing these weird teardrop sort of shapes. And that's because we're not blanking. We're simply going to set our fill style to black, and then we're going to call fill rect, and that's going to draw black rectangle. Now this is different than our other functions, as it just goes ahead and draws a raster rectangle. And what we're going to do now is, before we draw all of our particles, we're going to go ahead and call clear. So let's rerun this. And now we see as we click, we still create motion, we still create growth, but we are redrawing this each time. So when we click, we're making our particles grow, but every time we move our mouse, we're updating this mouse vector. What are we going to do with it? Well, eventually we're going to make these particles swarm toward our mouse, but that's a lot to do all at once. So first, let's visualize each particle's heading toward the mouse. We're going to do this by taking our mouse, and each time we're going to subtract the particle's position vector from it. And what that's going to give us is a vector that describes the difference between the particle's position and the mouse position, which means it will give us the exact vector we need to draw a line from the center of the particle to the mouse pointer. We're going to use that vector to draw a 20 pixel long line indicating the direction of the mouse pointer on each of these. So let's get started with that. First off, we're going to add a function called setHeading. Okay, so setHeading is going to create the vector that points from our particle to our mouse pointer. So we see here that the first thing we do is clone our mouse pointer. This is important because the vec2d library, all the functions, all the vector math functions, they affect the vector in place. So if we don't clone our mouse, when we do the subtract function, it's going to return the result of that subtraction vector, but it's also going to change the mouse vector to be that result. So the first thing we need to do is just go ahead and clone it, and then we can subtract from that mouse vector our individual points. After we do that, we're going to normalize it, which basically removes the magnitude. We're going to keep the ratio between the x and y components, but we're going to scale this down such that the direction is 1. A normalized vector is basically a vector describing the direction of something, but we didn't have to use trigonometric functions to get there. So then let's go ahead and add the setting of this heading to our step function. And we're going to do it right before we draw a particle. We're going to set that heading. Again, call by reference, modified in place. So by the time we get to draw a particle, if there hadn't been a heading vector already, there is now. Okay, so to draw this heading, we're going to set up our, we're going to add some code to draw a particle. What this code is going to do is it's going to create a new vector from our heading called terminus. And all terminus is our heading vector, which describes the direction toward our mouse, but it describes it sort of in a relative sense. So it describes a line, but that line points from the point 0, 0 in the direction of the mouse from the perspective of any given point. So if the mouse is up and to the right from that point, the vector is actually up and to the right from point 0, 0 and is of magnitude 1. So we're going to go ahead and multiply it by 20. We're using mul s here, that s is for scalar. This is different than multiplying a vector by another vector. We're just taking all the components of the vector, multiplying by 20. And then we're adding that onto the end of that particular particle's position. So terminus becomes the second x and y coordinates for a line that we are going to draw from the center of that particle. And we do that by beginning a path, moving to the center of the particle on this line, and then we draw a line to that terminus point. And then we set our line width to 2 and our stroke style to white, and then we actually stroke that line, which is when it's pushing the actual pixel data down onto the canvas. So let's see that work. That's pretty cool. And when we click, we still see that they shift and they grow. We're still pointing toward. And this shifting and growing thing is kind of silly. So let's do something a little bit more useful, a little cooler. Let's actually make, when we click, the particles go in the direction that they're pointing. So to do that, we're going to write a new function called jump. And this new function looks a lot like the drawing function that we just described. Here in the drawing function, we're cloning our heading and then scaling it by 20 and adding it to the position here. We're doing the exact same thing here. We're scaling it by 5 because I don't want to move 20 points at a time. And after we get that vector, instead of using it to draw a line, we're simply going to alter our point's position by setting it there. Our jump function is what we're going to call when we click. So instead of grow, put jump down here. And let's just get rid of our grow function. We don't need that anymore. And look at that. Every time we click, now these vectors are getting closer. But yeah, that's pretty cool. We've got motion now. We've got a system that is actually acting like a swarm. So what happens then if, instead of calling this jump function every time we click, let's just call it as part of our step function. We'll leave it for click too, but after we manipulate all our particles, let's go ahead and just call jump. Now let's run it and see what happens. Now we have all our particles moving very swarm-like, but very slowly as well. So let's go ahead, go up to our config, and let's crank up our frames per second now. Let's do 20. And now we have a swarm. Kind of a boring swarm though, because once these things kind of group up, they're not doing a whole lot. Just follow our pointer. But this would be much cooler if, instead of moving at a fixed increment, we treated these more like vehicles that have a certain amount of acceleration, that have a top speed, and that don't turn necessarily on a dime. Let's get to doing that. So far, our text has been teeny tiny. I'm increasing the size a little bit now. And let's close the CSS. We don't need this again. Bigger text. All right, good. Now let's do some more interesting things. We're going to go back up to our config and we're going to add some new values called speed and acceleration, or speed and ac. Our speed is going to be our particle's top speed, and we're going to put a little bit of variation in here because that makes our particle swarm more interesting. And our acceleration is going to be the amount of velocity that we can add to our particles on each turn. Up until now, we've been using vectors to represent position. Now we're going to start to use vectors to also calculate velocity. We're going to use the same sort of math that we used to describe our heading, except now we're not going to just move toward that heading. We're going to take our particle's existing velocity, whatever that may be, and we're going to add to that velocity some amount of acceleration toward where we want to go, in this case the mouse pointer. So the first thing we want to do is when we create our particles, we want them to have speed. We want them to already be traveling at some sort of speed. So when we go up here to our make particles, we're going to go ahead and create, and like everything else, we're going to use our little handy rand range to grab a nice random number for speed. Then we're going to add a few more properties. We're going to add this property trail. Trail is going to allow us to use whatever our last position was, and instead of drawing a point, we're going to draw a line. So we have a much more continuous sort of motion to these points. I think it'll become more obvious when we actually do it. But more importantly, we are going to add velocity. And for velocity, we are going to create a new vector, and we're going to point it in some random x and y direction. We're going to normalize this vector after we do that, because we're basically creating a random direction. Then we're going to normalize that, and then we're going to multiply our particle speed. The speed configuration here is actually the top speed of the particle. So all these particles are going to start out at their top speed. Acceleration is another scalar. It's the rate of change we can see in each frame. And then we're also going to hold on to this speed scalar. We'll need it later. So our velocity is a vector that describes how our object is moving every frame. Basically how many pixels left and right or up and down to move every frame. Our speed is just an aspect of our particle, like acceleration, that is going to tell us what our top speed is. Now we're going to add the most important function that we're going to call move particle. Move particle is going to work in a similar fashion to heading, except we're not going to set the heading and then use the heading. We're going to do that right inside of move particle. And what we're going to do is we're going to, very much like heading, we're going to calculate thrust. All thrust is again, we're going to look to our mouse, we're going to subtract our particle position from it, we're going to normalize it, and then do a scalar multiplication, just like heading, except this time we're multiplying it by p.acceleration. And we're basically generating a vector that is going to tell us how to move toward the mouse pointer by a small amount. And instead of moving directly to there, instead of that becoming our line of travel, we're actually going to add that to the existing velocity vector. So we've got a velocity vector that is describing how our point is going to be moving each frame. And then we add a small amount of acceleration toward the mouse pointer to that velocity vector. Then the last thing we want to do is make sure that velocity is not going over the top speed, because if we do, we'll have runaway particles. And then we simply add to our existing particle position that velocity. The velocity has already had the acceleration factored into it. Now the other thing that we did is set our trail position vector, x and y, to whatever our position x and y was right before changing position. So this is basically last frame's position, and this is this frame's position. That'll allow us to draw a nice line and smooth everything out, make it pretty. We're going to go to our step function. We're going to remove our call to set heading, but we're going to replace it with a call to move particle. And then we're going to change our draw particle function. We're going to remove this terminus code, and we're also going to get rid of our context.arc. So we're no longer drawing a circle and filling it in. Instead, our entire draw particle function is going to look like this. We're going to begin our path. We're going to move to wherever our particle just was, and then we're going to draw a line to where our particle now is. We're going to set our line width to the radius of our particle, and then we're going to set our color using our point fill function, stroke, to actually put the pixel data down. So what happens? Now we have particles with a little more interesting behavior. We can see that if we stop moving our mouse, they overshoot and then correct, and they orbit around, and they have this sort of jelly bean appearance to them.
because we're drawing them as lines now instead of circles. You might say, oh, I don't like jelly beans. Why are we drawing them as lines and not circles? This doesn't look any smoother. Well, let's see the payoff here. We're going to go back up to config, and we're going to add a new variable called fade. And this is going to change the way our screen blanking works. A fade of 1.0 is going to screen blank exactly the same way we are. It's going to say that this black rectangle that we draw is going to be fully opaque. It's going to refresh the screen every time. But if we change this to say 0.1, then every time we blank the screen, we're only going to use a 90% transparent rectangle. So we're going to retain most of the image that was there before. In order to make this work, we're going to need some code very similar to this, and we're going to call it our fade fill. Then we're going to go down to our clear function, and we're going to replace black with a simple call to fade fill, and we're just going to pass in config. And what we get now are some very pretty neon disco worms chasing our mouse pointer in very nice ways. And at this point, you could say your swarm is complete, and we can play with the values at the top of this file now to get all sorts of interesting things to happen. We can make our worms big and fat, and we can make them a little bit transparent now too. Let's move them a little bit faster, and let's definitely up our acceleration a little bit. We'll keep our fade where it is now. What does it look like now? Oh, that's kind of cool. And then if we don't like all those big fat particles, we can go just down to really tiny lines. Let's increase our number of particles. We'll get a completely different sort of shape here. Completely different kind of behavior. You can see here where we can kind of shepherd our pixels in, shepherd our particles in. So let's do one more cool thing. Let's we're not doing anything with our click function. Let's make our click function scatter our particles. Let's get rid of jump. We don't need it anymore. And let's get rid of jump there. We're stepping twice each time. Let's run our simulation again without that extra jump code. Yeah, we're a little smoother now. Whoops. So let's let that scatter function now. That scatter function is going to look similar to jump in that it's going to alter all the particles at once. But all our scatter function is going to do is randomly change the heading of these of the individual particles' velocity vector. This is the only place we're actually going to use a little bit of trigonometry math, probably. We're going to actually rotate the vectors. For every point, we're simply going to take the velocity vector and rotate it by plus or minus 180 degrees. We've got math, random, times 2 times pi. That's a full 360 degrees. And then minus pi, which is 180 degrees, basically, in radians. And we're going to run this, and when we click, we scatter. Let's turn the velocities down so that's a little easier to see. For our top speeds, we're going to take back down to 10 and 11 for max. It's not just 10 or 11, there's a whole bunch of float values in between those two. Okay, so here are all our points now. Again, completely different character, just from changing a couple of things. We see that they're clumping, and we don't want them to clump, so we scatter them. Every time we click, they scatter a little bit. Let's turn our acceleration down, but make it a little bit more varied than it is. Play with this endlessly. There's your particles. Hope you had fun.